Okay, so today we're going to be talking about a little bit more philosophical topic. Okay, so what does that mean? Well, we're going to be dealing with a situation where we're switching from forensics to security operations. This is a totally different mindset, and we're going to be focusing on gas phase detection. And the reason I put this in here is really more of an enrichment topic, um, because the same skills that you will use in a forensics lab you might be called upon to use in a security situation. So today we'll talk about the difference in forensics and security. Okay. So the role of security operations is different than forensics. The goal is to reduce a threat before the threat is carried out. Okay. Think about a forensic mindset. You're applying law to a criminal situation, perhaps. And so you're after the fact. You're gathering evidence. Your information and data is going to go into a courtroom to prosecute, but the event has already happened. We don't want that to be the situation in security situations because we don't want the event to happen. But yet it's the same kind of tools, a totally different legal framework, but the same kind of tools. And since y'all are the folks that are being educated to use the chemical detection tools, you may find a fulfilling career in security operations. It's the same skills. So that's why I put this in here, because this is a whole new branch of employment that you might find like fulfilling. Okay. So so the three Ds. Well, first of all, is to detect threats or threatening events before they happen, or the supporting infrastructure for a threat. So the first D of the three Ds is to detect. Okay. The second D is disrupt. So if there's a threatening event, there's a plan for it or whatever, you want to disrupt the capability of that threat to be enacted. So disrupt those threatening events and the supporting infrastructure. The supporting infrastructure is a big piece. It may not be necessarily your piece. A lot of times that's the financial side of things. And so we see these financial networks and requirements of banks to flag suspicious activity reports. So somebody's moving a lot of money and the bank has this criteria, and so they will file a suspicious activity report. And that's trying to disrupt the supporting infrastructure for these kinds of events, whatever they might be. Okay. And then the last one is to destroy those threats or the supporting infrastructure or the supporting environments. So, um, so these are the three Ds that are used worldwide, not just in this country, but everywhere. Because again, if you're trying to stop something bad from happening, these are the three ways you do that. If you can't detect it, it's difficult to disrupt it. And it's certainly difficult to destroy that infrastructure or that process. And so we're going to really focus on the detection today, that piece. Okay. We're not going to be the ones going out to disrupt things or to destroy things, but we're going to be on the detection side of things. That's the same skill that a forensic chemist would use in the lab. And the secondary goal, of course, is to minimize impact on normal life. So we don't want to turn the world into a surveillance state. You see that tension today, right? We want to be safe, but that requires interference in our normal lives. Okay. So if we go too far on the safe thing, we've locked everybody down and we lose freedom. If we're too far on the freedom side, then we're not safe. And so this is a complicated, that's why I said this is a more philosophical talk in this balance between safety and freedom. So what is a threat? This is also very good to think about too. What is an actual threat? Okay. It's not just threatening words. It's intent plus capability. Okay. Intent plus capability. So there can be lots of intent to harm you or your neighbors. You could have a personal enemy. They could intend to do you harm. Okay. When I was little bitty, my dad's he taught baseball. You know, he was a coach and taught baseball. That's funny. He was a coach, and his teenage teammates would tease me as like a 3-year-old or 4-year-old, and just tease the coach's son, and I would be enraged, and they would just tease me, and I would just be so mad. I if I had the capability, I would have killed them. Right? I was that angry, but that's a perfect example of the intent, but not the capability. I had the intent to do them grievous harm, okay, but I was for, okay, and it wasn't much I could do. So it's not enough to like just have intent. You also have to have the capability. So those two things are very important. Um, and so this capability, many capabilities exist to harm a single person. So it's impossible to get rid of all capabilities, right? In the UK, they banned handguns, and so the knife crime goes up. So what are they going to do? Are they going to ban all knives? Well, you got to cook, you got to cut onions, you got to do things in the kitchen. So it's hard to tamp down on all the capabilities, especially person to person. Okay, so we're going to have to look at larger capabilities that could harm large groups. Um, and so this is, again, if you have intent and the capability, then you have to look at where we're going to put our security resources. And so we put a lot of security into the valuable targets, which would be things like this. Large numbers of potential victims, like a sporting event and so on, a confined area, a controlled and predictable environment, and a highly symbolic target, and a large potential of media exposure. So these what would make an attractive target to someone wanting to harm a lot of people and get a lot of press and so on. And so these describe big sporting events, business buildings, airports, and so on. And so you know this, but this is obvious. This is what the security apparatus is thinking about. I was really surprised at how they changed uh, like the New Year's celebration at Times Square after 9/11. Okay. So it used to just be chaotic. Everybody would just pile into Times Square and party, and then the ball would drop and everybody'd scream and then they'd go home. Okay. But it was just jam packed elbow to elbow. And I thought, how are they going to have security for that kind of event? Okay. They put metal barriers up and made little squares, little boxes. And so then you bought tickets for the boxes. And so there was vetting of everybody that got there. And they knew where they were going to stand and all of that. So they turned it into a much more rigid environment, but yet just providing the ticketing, the vetting, the metal detectors to get in and so on, they were able to turn it into a safe event and still have a big event. So you see some of that stuff today if you go to concerts and things like that. The security folks are trying to look at these areas of concern. So let's talk now about what are some of the terrible capabilities that are out there to harm large groups of people. Things like chemical warfare agents. These are organophosphate nerve agents. I've got the structures on the next slide. I added a slide this morning. What these do is they inactivate acetylcholine esterase. So acetylcholine is one of the neurotransmitters from nerve cell to nerve cell, and it comes out of one nerve cell, goes to the other, and then you got to be able to turn that signal off. And so this enzyme breaks that molecule and turns off the signal. So you think about electrical signal, you can turn it on, but you got to be able to turn it off too. And if our bodies tells our muscles to go, stretch, and then we can't turn that signal off, our muscles are just locked up because we can't turn that signal off. And that's what these nerve agents do, is they will cause severe central nervous system disruption, and it affects our muscular system. And when it gets to our soft muscles, like our breathing muscles and our heart muscles, those things turn off too. And so this is what the nerve agents do. Vesicants are terrible too. They don't affect your central nervous system. They affect your skin and your lungs. And so these are blister agents, and surprisingly, very simple looking molecules. I'll put a slide in for those molecules this morning too. Now, the benefit to you as a forensic scientist is these are all volatile. So vapor detectors can detect these way below their toxic levels. And so if you're in a subway in New York or DC and you're walking through the subway station and so on, there's lots of little power boxes on the wall, circuit breakers and so on. Some of those boxes are sniffers. They're sniffing the air to see if somebody's released one of these in the subway. So they can be detected at really low levels. So these are the chemical warfare agents, and you can see they're organophosphates with organophosphorus compounds. And so now a lot of these are odorless and tasteless. So you wouldn't know that you got, splashed with it or sprayed with it. It's not going to smell, but they can be detected by our vapor detectors. And then these are the vesicants, the blister agents. So you might hear of a sulfur mustard gas or a nitrogen mustard gas. Really simple looking molecules. It's hard to believe that something looks like so common that you might see in a chem lab could be so dramatically devastating to your skin. A lot of people have survived mustard attacks. This was World War I was really what shocked the conscience of the whole world because of the use of chemical warfare agents. They put them on artillery shells. They sprayed them on the enemy in trench warfare. Sometimes the wind blew it back on the troops that were using it, so it wasn't as easy to use as they thought. But the dramatically awful way of dying from these chemical attacks has shocked the conscience of the world, and it's not been used in any of our, like the Gulf War or any of it really wasn't used in World War II very much that I know of. It's like I said, it was so gruesome that it shocked the conscience of the world, is how bad these things were. Now the blister agents, a lot of times people die from secondary infection because it ruins that boundary between our bodies and the world. And so bacteria and so on, we're very susceptible to that if we break our skin in dramatic ways. Then we have toxic industrial chemicals, these choking agents and so on. Again, some very, very simple molecules. You've got to be careful in some of your synthetic routes and so on that you don't produce these. Like some of these compounds can be fairly easily produced that can be extremely toxic. That's why we work in hoods, but we even still don't want to produce these because we don't want to blow them out the top of the building and affect anyone else. Now, once you dilute these, what is our phrase from about 2 weeks ago? The toxin is the dose. Yeah, exactly. So when it's diluted, I mean, it's not great, but it's not going to harm you. Your body will be able to handle the insult. But anthrax would be a biological. Yeah, so there would be spores of anthrax. Um, it's not a, I would say it's not as much of a concern as some of the other biologicals, but yeah, anthrax is really bad at wounds. Like you can get anthrax in your wounds. It's in the soil in some places. I don't know much more than that. I know that it is in the soil. It occurs naturally, and you can get it in an open wound, and it can make it much worse. They talk about weaponized biologicals like anthrax and so on, these spores. And what they do is they try to make it into such a small particle that it doesn't settle out. So most of your particles settle out. If I spilled sugar or flour on the table here, you'd see a little puff of cloud and then it would settle. Okay. But if you ever open a packet of, like I have these little emergencies, these little this vitamin C and like some raspberry flavor or whatever. And when I'm getting a cold, I take one of those. That is weaponized powder. As soon as I open the packet, I smell it. The particles are so small. They've been freeze dried. So they made up this stuff and then they freeze dried it, and that can make extremely small particles. So I open that up and that little puff of powder comes out and you can smell it in the whole room and it doesn't settle. So it's a micronized powder. So that's what they mean by weaponizing something like anthrax, is to micronize it so it doesn't settle. Let's look at more of these toxic industrial chemicals. They're much easier to obtain. For example, ammonia, farmers use large tanks of that. Swimming pool facilities contain large tanks of chlorine. If you're in a residential pool, you have these chlorine tablets that you put in the pump and so on. But if you have like a city pool or whatever, they typically do direct injection of chlorine into the water. So they'll have tanks of chlorine. And so that's it's really, really dangerous and susceptible to being stolen. And so these are toxic enough to kill if the dose is high. So what it does is these gases, many of them will get into your lungs, and they're soluble in water, ammonia and chlorine, and so then you have it damages the lung tissue, and it's soluble in water. And you have osmotic pressure, so your bloodstream, the liquid in your bloodstream wants to dilute the 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 concentrated acid or concentrated base in your lungs, and so your lungs fill with water to try to dilute that acid or that base. And so that's chemical pneumonia. Pneumonia is when you have water in your lungs. This is chemically induced pneumonia. While we're on the topic of pneumonia, there's another kind of pneumonia that's popped up in the last few years. I haven't heard recently, but like maybe 2 years ago, it was really bad among high school students, and it was called lipid pneumonia. Now, where would you get lipids in your lungs? Who's breathing oil? I mean, they're making a bunch of bacon and breathing in the vapors. I mean, there's oil vapor with bacon, but you got it right, vaping. So they're overdoing it. They're over vaping because they're young. They don't have executive function in their brain, and they don't limit what they're doing. And they were getting coalescing oil droplets in their lungs, and lipid pneumonia is awful because most of the time when you get liquid in your lungs, you dehydrate your body with diuretics, and you just use the Chatelier's principle to pull that water out of your lungs. But what are you going to do to get oil out of your lungs? It's a really big problem. So that's a real issue with vaping, especially with young kids. Now, again, if you need a lot for a toxic dose for a lot of people, this is going to be hard to do, right? So that capability just naturally is hard. You may have the intent to cause harm, but if you're rolling into a business building or into the basement with 8 tanks of chlorine, and you're hooking them up to the ventilation system, it's going to be conspicuous. It's going to be detected, okay? And so also these volatile toxic industrial chemicals are easily detected. A lot of large buildings have detectors in their HVAC system. And so if they smell chlorine gas, they shut off the HVAC. And so that protects the whole building. And of course, ring the alarm, call the cops, and so on. That's all plugged in. Let's look at some of the data from an old, I mean, this was, I was in my freshman year in college, this happened. So it was a while ago, 88. But I still have this in the notes just because it's impressive to see how much evidence was left behind. So this was a 16 ounces, one pound of plastic explosives brought down a whole airplane. So that killed 243 passengers, 16 crew, and then 11 residents on the ground in Scotland. Okay. And so let's look at some of the where the evidence was in this situation. So this debris field was over, a village in certain areas in Scotland, and they came and got all of the debris and took it to an airplane hangar, and they laid it all out and tried to figure out, what caused this airplane to crash. They figured it was terrorism, but they wanted to figure out what it was. They found a 20-inch hole in the forward cargo hold. So this wasn't in the passenger compartment, it was down in the cargo hold. 20-inch hole. So they found, the skin of the aircraft had been ripped open. So that was an event inside the cargo hold that blew out. An examination of the baggage containers revealed higher energy damage. So they found the bags nearby or that contained the explosive, and they could see that it was high energy damage, meaning an explosion had happened. Test explosions confirmed the location and quantity of the explosive used. So they had to come up with a little research experiment. Let's put half a pound in a bag, a pound, 2 pounds, and so on, and see what kind of damage this caused. And they say, okay, this was about a pound of explosives. And then this is some of the evidence that they got, which is surprising to me. So they found a Samsonite suitcase that they thought contained the bomb, and they recovered pieces of a circuit board, okay, which was part of a Toshiba bomb beat radio cassette player. Have y'all ever seen a cassette player? You ever seen the Walkman, the Sony Walkman? This is the Toshiba version of that. It's a little cassette player about that big. I had one, okay, and so they took the guts out and filled it with plastic explosives, a pound of explosives, and then they found also this was similar to one used to conceal a bomb seized by West German police in a terrorist attack 2 months earlier. They also found a circuit board fragment embedded in a piece of charred material that was identified as part of an electronic timer. So see, it's amazing how much evidence is left behind. This was right next to the bomb. This was the circuit board that set it off, and yet there's pieces of it left. So we think of explosives as completely consuming things. They do not. It's hot gas. Yeah, there's a shock wave and it breaks things, but it doesn't just like consume things. A nuclear blast would, but a chemical explosive just pushes stuff around and burns it. Okay. And so there's a lot of evidence left behind. And there's also a lot of unexploded uh, explosives on these different parts. If you can swab it off and you could test it. Okay. And so they finally pieced together this unaccompanied bag had been put into the system. I think it was, yeah, from Malta, okay, no, from Lucca through Malta and to Frankfurt, and then from Frankfurt to Heathrow. So this was like two legs along, and this bag is sitting in the hold the whole time. So what have we done airline wise? You know, we ask everybody, has anybody had access to your bags without your knowledge? You say no, okay. And then you're not allowed to check a bag to a destination and not get on the same plane. That's a big deterrent, right? I mean, if I could just send a bomb with the plane and not get on the plane, you know, that's different than actually having to be on the plane with my bag. And so they've switched that where you're not able to check a bag to a destination and not also board. Yes. Interesting. Yeah. So that's one of the ways to make an explosive powder, specifically a powder, safe, is to keep it wet. So at Pantex, all of our explosives were stored in water. They're organic compounds, they're not soluble in water. And so we would have our explosives stored or safed in the safe, our explosive compounds that were wet. And so the first thing we would have to do if we were doing a particular analysis was to dry that out in an explosive safe oven and so on. But we would only do small amounts, you know, for lab testing. So you could take out a half a gram or less and put that in a container, and then you could put it in the explosive safe oven, set a timer, and come back, and you'd have your dry explosive. You could take infrared spectra or whatever you wanted to do with it. And so that was our whole method for making explosives safe in the lab, was to keep them, transport them wet, keep them wet. The problem with TATP, so y'all need to write that down. TATP, it's so dangerous that there have been examples of it exploding while it's wet. Yeah. So I had a research project at Pantex where I was going to do spectroscopy on TATP and try to get some infrared spectra, some Raman spectra, and so on to help detect it and so on. And Lawrence Livermore National Lab, who also works with explosives, put out a bulletin on the national the national labs communications and said uh, we had an example of TATP exploding wet, and so my project immediately went to computational chemistry. So I was not going to handle that explosive in our lab because I didn't know how to keep it safe. I wasn't going to blow my hand off, and I figured I would simulate the spectrum and at least contribute that way. So that's what we did. Let's let the experts at Livermore handle it. Okay, so let's do a Kahoot to wake us up this morning. And this is a review of the combustion and explosives stuff that we did last time. 31. Where are my pancake hands? You got the little graduation cap on. Very nice. That's right, exactly. Bring it to me. Couple more. Uh-oh, we're going down. Okay, we'll get started. There'll be a code at the bottom. You can join if you got kicked off. What part of the fuel triangle chain in this conflagration? So don't do this. You try to drop water on an oil fire. Did it freeze? No, we're just waiting. Our music went away. Okay, there we go. Yes, mixing of fuel and oxidant. So what's going on here in this oil fire? We've got oil burning, we've got air as the oxidant, and he dumps water on it. So why is that a mixing effect? So do you know, I mean, what's the boiling point of water? Yeah, 212. What's I know like 100 C. Oil, a lot of times oil doesn't even boil. It gets up to 300 and it starts to decompose. Okay. So oil can be much higher in temperature than the boiling point of water. So let's say your oil's at 200 C and water's boils at 100 C. You dump water into 200 C oil and it goes to steam. And so the steam blows all of that oil out and it's already hot and it's already burning. So you now have vapor, oil vapor. And that's what causes this to completely go up. Okay. So that's a real risk. Um, when you put a turkey into oil, you're going to fry a turkey. What's in all of that skin and all of the flesh and stuff? A lot of water. So you put a turkey into oil and that water starts to boil. That's what the bubbles are. You do that too fast, you got a flame underneath, you see the same thing. And there's lots of videos about that. You're laughing. What's going on? What? Did something? Oh, okay. I didn't know that was a capability. Yeah, so that's something new. Yeah, that's good. Yay, thanks for clapping. That's good. I won't take those personally. No, don't be mad. Okay, very nice. Okay, number two. What's the major difference between detonation and burning? I think I've got some duplicate questions in here. Can you answer? Nobody's answering. They're probably it's so loud. I didn't know that I would have sound on that video. What? You all stink. That was mean. Yeah, man, what's going on here? IT, did you cut me out at the knees? Come on. It says it's connected. Did it go now? I don't know how to restart the thing. Okay, well, we'll just go on. See if it'll let me. Okay. Now let's see if you can remember. It's testing your memory. We would be in trouble if it was 100%. Cigarettes wouldn't last as long, that's for sure. Yes, 20.9. The green one is nitrogen. So if you couldn't remember the difference between oxygen and nitrogen, the green one is the nitrogen. Okay. How many liters per mole at room temperature in 1 atmosphere? So we did this in the calculations. You may have learned one of these numbers as a freshman, but it's slightly different at room temperature. When you learned at the freshman level was STP, which was 0 C. So one of these is at 0 C, the other one's at 25 C. Yeah, so 22.4 is the 0 C, it's STP. 24.5 is SATP, or ambient temperature and pressure. Okay, okay. That was so painful. What is the perfect ratio of fuel to air called? Pretty even split. Look at that. It's the stoichiometric ratio. So that idea of stoichiometry, that's that balancing of the moles of this and the moles of that. So the perfect mass to air ratio of fuel to air is the stoichiometric ratio. If you have that, then you have an explosive situation. It may not detonate, but it would be an explosive mixture. And so that's what we call the danger zone, is when your air or fuel to air mixture is at the stoichiometric ratio. Blank is when the burning energy wave is less than the speed of sound. I should say slightly less, but I wanted to keep it short. So it's getting close to the speed of sound, but it's slightly less. Good. Deflagration. And then those of you that picked the green, um, be like this. Blank is when the energy shock wave is faster than the speed of sound. Fast thumbs. And then the one person that's just waiting. Can you do the faces now, or is it only like afterwards? Okay, good job, 100%. Yay, next. Okay, we still got the fastest thing. Which explosive is often found in ammunition primers? So this was a random fact that I threw in. I had all the explosives there, and it leaves behind a residue that's easily detected for gunshot residue. So that's a hint. Good, lead stiffnate. And that lead is left behind a lot of times. Little molten particles of lead oxide that end up on your clothing, on your hands, and so on after you shoot a firearm. All right, let's see what we did. Yay. Good job. Take it. Oh, two top hats. Very good. Well, there's like real applause on there. Did you hear that? Okay. Okay, good job on that. Bit of a review. So now we're going to get into the detecting of these indicators of threat. So volatile compounds are indicators of a threat, like chemical warfare agents or toxic industrial chemicals. And these are easily detected by gas phase detection methods. Okay. We also have explosives. They might indicate a threat. And how might they be detected? Now, there are legitimate uses of explosives. So if you found a vehicle that had placards and so on, it had explosives in it. Do you know what are the uses, like the legitimate uses of explosives? What? Yeah, mining is the big one. Military, of course, but mining is the big one. So explosives for mining, we still use that. We also, in some law enforcement situations, they have explosive door penetrators. And so these are things on a paddle. They're shape charges on a paddle that they can put on the hinge area, and they can pop those hinges, and the door just breaches wide open. So you can have all kinds of deadbolts and so on all up and down the closing side, and they blow the hinges, and the door swings wide open. Okay. And so, there's companies that manufacture those things, so they would have a legitimate reason to be transporting explosives. But there's all kinds of regulations on how you would transport explosives, and you would check their manifests and their, placarding and everything like that. And so, what are these explosives? Well, they're energetic materials. We talked about this last time, where the fuel and the oxygen are present in the molecule themselves or in adjacent molecules in a solid. So the explosives must be safe to be useful. And so this is the reason why sensitive primary explosives are often too dangerous to handle. Um, like mercury fulminate or even nitroglycerin, this sensitivity 0.2, that's ridiculously small. So a small shock to nitroglycerin can cause it to detonate. Now, if you mixed it with diatomaceous earth, stabilized it, then you'd have dynamite, and so then it would be less sensitive, and that's the reason why you would mix it with diatomaceous surface to make it uh, not very sensitive, but move it into the sensitive category. Secondary explosives are less sensitive to detonation by dropping or static charge and so on. And this drop hammer test is used to rank sensitivity. So that's what these numbers come from. These numbers come from the drop hammer test. And these last two are very common. Ammonium nitrate mixed with fuel oil. That's ANFO, ANFO. So this is fertilizer, ammonium nitrate fertilizer. So people can find that in the agricultural situations, and they can mix it with fuel oil, which is diesel fuel. So you're mixing ammonium nitrate and diesel, and now you've got an explosive, and it's an insensitive explosive, so you can drive it in a truck and bounce over potholes and all of that. It needs to be detonated by an explosive, so you have to have an explosive to set it off. Now there are situations where ANFO has detonated from like a fire. So in Waco, this was several years ago, there was a fertilizer plant at Waco that had improper storage of its ammonium nitrate, and the place caught on fire. Okay, and so it was burning vigorously, and it was not confined originally, like it's just in a pile of ammonium nitrate, but started burning from the outside in, and the heat wave going into the material acted like confinement, and it reached the point that energy wave started moving faster than the speed of sound. We got a detonation, and the whole plant detonated and destroyed the whole front of a high school and a lot of facilities around it. And my cousin's kid went to that high school. Yeah. And she jokes that he graduated because all the records were destroyed. I don't think so. He's a pretty bright kid, but she was always joking around. She's like, "Yeah, he graduated because they destroyed all the records." But the TATB is a very important explosive. It's used in a lot of our explosives, and it's insensitive too. So I mean, they can take the main charge and shoot it with a 50 caliber a gun and it not detonate. That's not enough of a shock to get TATB to detonate. Okay, so that's an incredibly safe explosive. This is the drop hammer test. It sounds funny, drop a hammer on something, but it's kind of that way. They built this little tower with ball bearings and so on, bearings, and they have a weight and they release it and it falls down and hits the explosive. And the explosive is on a little bit of sandpaper. And how do they know if it detonated or not? Well, they have a microphone and they listen. So they do a control and they get the sound of the hammer. Okay, that's what the sound of the hammer looks like. And then they put explosives in there and they come down and it's a lot louder. And they're like, okay, we got a reaction. They also have a camera on it to see if they see light. And so there's different grades. There's certain heights, they'll get a little bit of light, but no real percussion sound. And then they'll be a little bit higher, they'll get both. And so they'll have a threshold and they'll say, we dropped it at these different levels, and they'll come up with a threshold where above this threshold you have a 90% chance of detonation. Below this threshold you don't. So that's the drop hammer test. Now, these explosives, if you're a user of explosives, legitimately you would like to only use insensitive explosives, but they can't be detonated independently. So you need to have a detonator. So that's why we have these extra detonators. You have the main charge and the detonator. And so this explosive train is needed. You need an initiation event, the primary charge, and the secondary charge. And so these are non-volatile and very safe to use. So the bulk of the explosive is safe to use. The detonators are less safe to handle. And the detonators are volatile. So even though it's a few grams in size, for our detection techniques, these detonators really stink. And so we just deal with, like, thinking about our noses, right? You could have just a tiny amount of, like, you ever in middle school or whatever have some kid bring stink bomb to school or whatever, like the sulfury compounds, rotten egg smell, it doesn't take much, right? And you can evacuate a room. To our detectors, these detonators are like stink bombs. And this doesn't smell at all. And so even though there's so much more of the main explosive, the detectors are what we smell with our equipment. Now, explosives must be detected. We could detect them gas phase wise, or we can even image. And so imaging techniques like X-ray and terahertz, we don't like to use X-ray because it's ionizing radiation. And so that can expose typically the workers who are working around it. They're at the most risk. That's why the dentist gets you all set up and goes behind the wall and punches go on the X-ray, because they're lowering their dose. Terahertz is like radio wave, between radio wave and microwave energy. It does not ionize any water. It's not strong enough to ionize molecules or anything like that. It does reflect off of water. And so it takes advantage of the situation where our bodies are mostly water and our clothes don't really have any water in it. And so it goes right through our clothes and bounces off the water in our bodies and comes back to the detector. So if there's anything dense between the detector and the source, it will show up as a shadow. And you can see this person is sort of I don't know that this image is real, but it's sort of showing their capabilities. Like this person, you see this dark area here, and it's showing that this person has something under their shirt. And so you just pull that person aside to do secondary screening. So this is very fast, right? It just flags people for further inspection. So you can have terahertz detectors looking through people's clothes, and that was controversial because you could see their anatomy. And so you don't want a bunch of creeps looking at a bunch of people's anatomy all day. But that's that balance of being safe versus, freedom and security and privacy. So there's been some modifications to the system to like shade out faces and things like that. So that's terahertz spectroscopy. We could detect explosives with dogs. So again, dogs can smell much better than we can. And so they can certainly smell that PETN in detonators. So that I want you to connect the explosive pentaerythritol tetranitrate to detonators, because that's one of the most common detonator explosives. And then this dinitrotoluene is an impurity in trinitrotoluene. So when we don't completely nitrate the toluene, we make 2,4 dinitrotoluene, and so it's more volatile than the trinitrotoluene. So even though we have a main charge that's mostly, say, 99% trinitrotoluene TNT, there'll be a few parts per million, maybe 200 to 400 parts per million of dinitrotoluene, and it stinks enough that we can detect it with our detection equipment, and dogs can smell it too. They can be trained to smell it. Okay. And so we also then have instrumentation, GCMS, and all kinds of other techniques, which we'll look at in a second. So let's look at tunable diode laser absorption spectroscopy. This is what I used in my graduate work for writing my thesis, and it was extremely sensitive and extremely selective, which means it can pick a compound out from many others, okay, but it's super expensive and it's not commercialized. Like you can't buy a system in a like contained box. This was out on the laser table and was basically homemade at a national lab. GCMS is the gold standard, but it's way too slow. TSA for airline screening wants there to be 6 seconds per bag. So think of that. That's not long at all. So the swipes, they wipe the bag and they put it in the machine. It needs to give a yes or no in terms of risk in 6 seconds. And so that's too fast for GCMS. We could have long path IR. It's less sensitive, but it's very selective. The terahertz screening, we're only using terahertz to image like dense objects on a body. We're not detecting what those objects are. So it would be nice if we could develop terahertz also to look at the rotational structure of these molecules, but so far we don't get any spectroscopic information out of terahertz spectroscopy. Dogs are expensive, not just because the dog has to be trained, but you have to put a person with that dog too. They always have a handler. And so you have the dog who's gone through this extensive training, and you got to pay the handler a full, fee too. Their lifestyle. I mean, they're full-time employees as well. And then we have adsorptive techniques. Now these are interesting. You can take polymers and their stretchiness or whatever physical properties they have, and you can put, let's say we're going to detect TNT. So we have this polymer, we warm it up, we clean it off, and we measure its stretchiness. And then we expose it to TNT. So you have TNT molecules on that polymer. And then we coat it with another polymer. And so now the TNT is trapped between two polymers. Okay, and we measure its stretchiness. Then we warm that up and the TNT leaves. And what does it leave? It leaves a perfect hole for a TNT molecule. So now this polymer and its stretchiness is like an electric nose. So you might have heard these things called electric noses. It has a receptor that fits a TNT molecule. It doesn't fit a PETN. It doesn't fit a TATP or any of these other molecules. And so that's fantastic. You want to talk about selective, only TNT will fit in that little hole in those polymers. And its stretchiness will change with there's TNT or not. Now that's great, but you've got to make a polymer nose cell for every kind of explosive. And so making a range of detection is expensive because you have to have a polymer trained for every explosive. And so ion mobility spectrometry, this is the one that we've gone with. It has the advantages of mass spec and chromatography in one package that doesn't have to operate at a vacuum. So it was designed for the U.S. Army to detect chemical weapons and used by the Coast Guard to detect narcotics. And it's used in the airports all over the place. And then in our own university, we have this direct analysis and real-time mass spec. So it's a sniffer mass spec. So it instead of going through the GC to get to the mass spec, it just takes compounds directly in. So here's the ion mobility spectrometry, which we've talked about before, but let's look at it in terms of explosives. So the explosive molecules come in here. We have a nickel 63 source that's emitting beta particles, and they will ionize these molecules. And then they're attracted to this positive detector over here through air. And so they travel down, kind of like I said with the dance floor, to this detector. at different rates. And so narcotics typically form positive ions and explosive negative ions. And so for the first generation of these machines, you had to pick whether your detector was positive or negative. And so if you made the detector positive, then you were detecting negative ions. You were detecting explosives. And so they had explosive mode. And then if you wanted to detect drugs and narcotics, you'd switch it over to drug narcotic mode and it would detect positive ions. Now they make T-shaped, where they have a positive detector on one end that detects explosives and a negative detector on the other end that detects narcotics. And so this dual tube detection is the latest generation of these. And so we have these, this is what we call a plasmagram, and then we have this waterfall plot. And so you put that swab in there, it desorbs the molecules, and then you detect them. And so here's the criteria that we have. Here's for explosives. We have the drift time. So back here, that's this this drift time is down here, how long it takes to come out. So this right here is the drift time. So it took a lot longer for this molecule to hit the detector than it did for this one. Okay. So look at our explosives. You know, we have dinitrotoluene here, HMX, nitroglycerin, um, nitroglycerin and TNT mixed together, nitrates, and so on. There's a plus or minus variability. Okay, and then we have the full width at half max. So how narrow is the peak? And that's important because you don't want to have a big blob come through and hit the drift time, but its peak is too fat. If its peak is too fat, then you can't say it's that explosive. Then you have an amplitude. It's got to be above a threshold, and so it's got to be above 75 for you to say you've captured that particular explosive. And then it has to be in 2 or more consecutive segments. So these are segments, the number of segments. And so it's got to be repeatable. So it's got to hit multiple times on those segments, and it's got to be at the right location. It's got to have the right width. It's got to have the right amplitude. Once you make it through that filter, then you can confidently say, we have HMX, you know, ring the bell and call security because we got a suspicious package. It's really fun to go and get that ion mobility spectrometer that we have up in Forensic Science and swab our money. You put it in drug mode and swab your money and put the swab in, and almost every time you get a hit for cocaine or meth or heroin or whatever, because our money is so dirty. It's been used in the drug trade so much. It's really an indictment on our society, in my opinion. Now let's look at direct analysis mass spec. Okay, so this is really good. This is a previous student's thesis for the detection of explosives and explosive residues after the blast. And so they put all these pieces here in a little toolbox out at Gibbs Ranch. They put a explosive pipe bomb inside, and they back away and they detonate it. And then they go and pick through all of the debris, and they swab it and look for explosives. And so his thesis was detecting this both spectroscopically, and so these are micrographs of this pyrotechnic mixture. And so we have potassium nitrate here, barium nitrate here, and then this is a big indicator right here, the perchlorates. So perchlorates are very common. There's a lot of oxygen there. You can mix that in with a fuel, and you've got your oxygen and your fuel right next to each other, and it's very difficult or impossible to put out that fire. And then here's the Raman spectra. So the Raman microscopy, you can take this tiny little crystal. Look how small it is. This size bar is 10 microns. So that's about 15 microns across. You can't see that crystal with your eye. It's the smallest particle you can reliably see is around 200 microns. So this is 1/10 of that. Okay, way smaller than the width of a hair. Okay, And yet he can zoom in, he can focus his laser right here and get this beautiful Raman spectrum. And then this is the direct analysis time of flight spectrometry. So this ion source, kind of like we had in the ion mobility spectrometer, you could take a wipe or a swab and get your material and then desorb it with heat and then ionize it and then focus those ions into this chamber. And so when they flow into this chamber, you have a pulse of electricity. Let's say that they're negative ions. So you pulse this with a negative pulse and the ions go this direction. Now they're going to accelerate. F equals ma, right? And so you've got different masses. You give them the same force. If you've got a negative charge and you've got a negative pulse, you know the force that you put on that negative charge. But that negative charge is on a mass. And so you have this m over z ratio, the mass over the number of charges it has. And so then it accelerates at different rates. So your lighter molecules hit first and your heavier molecules hit last. And so you get a dispersion. So this is mass over charge. And so you have PETN plus a nitrate ion, PETN plus a nitrite ion, and then here's your PETN molecular ion here, and then here's your nitrate. So you can see we get adducts, which are two ions hooked or mixed, held together, and then you can have the molecular ion. Here's TNT minus a hydrogen, and then here's TNT molecular ion, and then here's TNT with minus a nitro group or a NO group. And then lastly, we get some of the more the ones I'm scared about. Okay, I'm worried about explosives. I'm worried about chemical warfare agents and so on. But the toxin is the dose, right? So even in a chemical attack, it's not likely that you're going to get a lethal dose. Okay, explosives. Once you're beyond the blast radius, I mean, you might have hearing damage and so on. Those are not to be minimized, but there's a certain radius at which an explosive attack could affect. Even a nuclear detonation has a radius beyond which there's very little damage and danger. There may be cancer risk long term from the fallout, but the thing that worries me, and that we just went through in 2000, was the biological situation. And so because these little critters multiply, and that's different than a chemical attack. That's different than an explosive attack, different than a nuclear attack. This can go global, and we saw it go global. Okay. Now, luckily for us, it's not easy to make a virus go global. It's hard to stop pandemics, but it's also really hard to create a pandemic with a high mortality rate. The reason Ebola hasn't wiped out the planet, why do you think Ebola hasn't wiped out the planet? Ebola is a virus that causes great hemorrhaging. So you bleed from every orifice in your body, eyes, ears, everything. It's deadly. What?
It doesn't spread as you speak.
Why not? Well, let's say they had an aspirable version of Ebola. So far, it doesn't spread, through the air. Okay, like would spread with bites from an infected primate. Okay, but why, if it were spread human to human easily, why would it probably still not go global? The mortality is too high, so it kills people off too fast. So if you wanted something to go global, you would need to reduce the mortality. But that's a good thing for everybody on the globe, is that the mortality drops off. At one point, the SARS-CoV-2 virus had a mortality rate of 0.5%. So 500 out of every 100,000. That's still way too many people, but it's not near as bad as Ebola. Okay. So also, the thing that makes biological weapons or pandemics the scariest is when they're first detected. What do you typically detect first? The first dead body, the alpha patient. And so at that point, you've detected a new pathogen and its mortality rate is 100%. So it takes time to figure out what the true mortality rate is in the general population. And so it always starts in a terrifying manner. It looks like it's 80% mortality rate. That's because we've had, 100 patients and 80 of them died. Okay, we only have 20 out of 100 that survived it. But once you get more data, then you get better statistics and you can determine what the true mortality is. And it depends upon age and it depends upon health factors and so on. So we saw all of this with COVID. Um, the thing that worries me is when people start to try to engineer these pandemics. And so I'm, I'm very against this enhanced, function virus research. We already know how to sequence all of these things. We already know how to produce vaccines and targeted responses to these. I'm saying I'm against doing research to make these super bugs just for research purposes because they're going to get out. And so anyway, I have nothing to do with trying to stop that except tell you I'm against it. Maybe you'll be reticent to do that. The difficult thing is when it goes human to human and people stop moving around and the weather changes and these things. Like if you were a terrorist trying to make a superbug, the thing that worries me is when they find a reservoir species for this pathogen. West Nile virus, you probably never really heard about that one. That was about 20 years ago. The first case was in New York. It didn't. It killed the guy because he was old. He was an elderly man. It's a virus that causes a tiny little rash, little pinprick rash that doesn't itch. Okay, um, and it made you feel fluish. Okay, body aches and things like that. You had a small fever, but then you got over it pretty quick. But then the complication is it could cause encephalitis, like brain swelling, water in the brain, pressure in your brain, and that can have dramatic effects if you're sensitive to that, if you're older, and so on. And so people could die from West Nile virus, but mostly they didn't. The problem with West Nile virus is it had a reservoir species and a vector, so it was spread by mosquitoes. And the mosquitoes die out in the winter, it gets cold and so on, but the reservoir species was horses. So the mosquitoes would spread the virus from humans to horses. Then those mosquitoes would die out. Then the next spring the mosquitoes would populate, bite the horses, get the virus, and carry it to humans. So the alpha case was in New York, and 2 years later I caught it in the panhandle of Texas. So this went over 2 years, real fast, spreading across the country. And so again, that's the worst possible case when you have a vector like mosquitoes and you have a reservoir species that carries it from one season to the next. And there really be no way to stop that except kill every mosquito and kill every horse. We didn't do that because it didn't have a high mortality rate. But that's how you would get a high mortality rate virus to go global, is to have a vector and a reservoir species. Because then it doesn't just spread on humans. If it kills out the human population in that local area, that would stop human to human spread. But the vector takes it to the reservoir, picks it up the next year, and starts it over. So those are the worst case scenarios. So hopefully I haven't scared you to death. In dealing with these things in the lab, we have different biosafety levels. There's biosafety level 2 hoods in labs and in biology and so on that can handle infectious diseases that have a moderate risk. But when you get up to diseases that can cause death or exotic high risk pathogens, then we have to suit up completely sealed up system and with the positive pressure suits, and so your suit is pushing out pressurized air, so nothing can get sucked in. And then you have a decon chamber where you go out of the lab and you're decontaminated, and you take off your biosafety suit, and then you leave in your civilian clothes. These pass-through autoclaves too. Everything that goes in and out is autoclaved. And so, parting thoughts. Pilots describe flying as hours of boredom interrupted by seconds of terror. And so the reason we did this talk today is because you're going to have the skills that definitely make you valuable in the crime lab for prosecuting crimes that have already happened. But those same skills are valuable to the security apparatus. And I just wanted to open your eyes to that possibility of using your skills. Okay. And so you will be thinking in the future of detecting, disrupting, and destroying these intents and capabilities, so that these days of terror are rare. These are the resources that I used in this talk. So, are there any questions? We've got about 2 minutes, 2 or 3 minutes. Y'all have, I mean, COVID, when did it hit y'all? What grade were y'all in typically? Junior high school, sophomore? Yeah, my son was a senior, so he came home for spring break. We went camping, and then he never went back. Right? That was so weird. Yeah, yeah, yeah. It was. We were hearing rumors of it around January. My daughter and I went to just tour Jerusalem and all of the holy sites and so on in January, like 1st through 15th or whatever, right before school started. And we came back and then everything shut down. It was crazy. So what? Yeah, that's right. 6 feet. We had a big screen. We had a big plastic thing here. I had a little mask on, like the little plastic face shield and so on. So I'm glad we got past all of that. All right. Well, you'll have a good day.